Hey everybody, so this is the solution video for Worksheet 2.2. We'll be talking about solving absolute value equations and graphing absolute value functions in this one. So let's start off with number one, part A. So we want to solve for x, and this is a nice easy one to get warmed up with. The absolute value of x is equal to 6. So before we get started, let's think about, just remember what the absolute value function really means, especially with something like the absolute value of x. This is actually a piecewise defined function, if we were to really define it. And the absolute value of x is defined as, because basically whatever you put in it, it's going to come out positive. So if you put in a positive number, then for any positive number or 0, we plug that in, we're just going to get that same number back. Whereas if we were to pick an x value that was negative, or put something in the absolute value function that was negative, we have to change the sign so that we would define that piece as being minus x. So if we put in negative 6, we'd have to take negative 6, multiply it by a negative to make it positive to come out of the absolute value function. So we're just going to kind of remind ourselves of this as we go ahead and solve this equation here. So we know that the absolute value of x is equal to 6. Well, this leads to two possibilities. That term, that x term inside of the absolute value function, it could have been positive x is equal to 6, or it could have been the negative version, and that's equal to 6. So now we've got two equations we solve for. So x could be positive 6, or minus x could be equal to 6. Which if we multiply both sides by a negative, we'd get x is equal to negative 6. So we have two possible solutions here. X could have been positive 6, x could have been negative 6. Kind of an easy example, we could have figured that out probably just by looking at it, but I think it sort of sets the tone for how we want to think about the next problems. Okay, so let's go ahead and try this next one, part B. So we've got a similar type of setup, except we've got the absolute value of 4 minus x is equal to positive 7. Now, as you can probably guess, like we did last time, we're going to want to break this up into two separate equations. But I wanted to make note real quickly that when you get an absolute value equation, even though it's not really an issue in A or B, the first thing you always want to do before you break it up is to isolate the absolute value, if you can. So sort of as a first step, we're going to go ahead and say first isolate the absolute value. And again, that's sort of if possible, but in this case it's not necessary. It's already done for us, so we can kind of move on from there. But I just wanted to make sure that was mentioned if it does pop up. So adding, subtracting, constants, multiplying, dividing to isolate that absolute value like we have here is really the first step. Now we can go ahead and we can break it up into two separate equations. So we've got the positive and the negative version of what's inside the absolute value to account for. So we have the positive version, 4 minus x is equal to 7, and then we want to consider the second one, which was that maybe that term is negative. So we'd have negative times the quantity, 4 minus x is equal to 7. And now we can just go ahead and solve each of these. I'm going to go ahead and distribute the negative on this. Actually, let's go ahead and solve the positive one first. So we'll go ahead and we'll subtract 4 from both sides. So we'll get minus x is equal to positive 3. And then we'll go ahead and we'll divide both sides by negative, or multiply, and we've got x is equal to negative 3. So that's our first possible solution here. On the second side, let's go ahead and distribute that negative. So we'd have minus 4, and then we have plus x is equal to 7. We're going to go ahead and add 4 to both sides, and we get x is equal to 11. And as is the case with all equations, it's usually a good idea to check these solutions, and these are pretty easy to do that. We could go ahead and plug in negative 3, we could go ahead and plug in positive 11 into the original equation over here, just to double check that these do in fact work out. And in both cases, these two solutions work out. So that would be our second one. Now for part C, we've got a little bit more going on, not too bad. But we're going to go ahead and we're going to go through the same sort of checklist. So first, is the absolute value isolated here? And it is. So right over here, we've got just the absolute value of x, and then everything else is on the other side of the equation. So we can go ahead and move on to the next step, which is to break it up into two separate equations. So we've got the positive version, x is equal to x plus 3, or that term inside the absolute value could have been negative. So we have negative x is equal to x plus 3. And then now we can just go ahead and solve these. Now notice what happens here. I'm going to go ahead and in this first one, I'm going to go ahead and subtract the x from both sides to get our x's on one side. And what happens is we get a 0 and 3. Now 0 is not equal to 3, and sometimes this happens, but this is actually not a solution. So we're just going to sort of ignore that one. Sometimes it happens. If it does, double check your work to make sure you haven't done something silly with your arithmetic. But in this particular case, that does not lead to a solution. So let's go ahead and check this one. So we've got negative x is equal to x plus 3. So again, I'm going to go ahead and subtract an x from both sides, which is going to give me negative 2. X is equal to 3. And then I'm going to go ahead and divide both sides by negative 2. And this gives me the solution x is equal to negative 3 halves. And again, it would behoove us to check this, so we could plug in negative 3 halves. Let's actually just sort of do that real quick to see how that works. So if we wanted to check this solution, we could go ahead and take the absolute value of our suspected solution, minus 3 halves, and just plug it in there, anywhere that there's an x, and see what happens. So on the left side, we get positive 3 halves. And if we take 3 and subtract 3 halves, that's basically subtracting 1.5, we're going to be left with 1.5, which is 3 halves. So this does check out. So you've always got that ability to double check in your back pocket with equations. Okay, so for this last one in part D, we can't really isolate the absolute value because we've got 2 of them. So what we're going to do is we're just going to go ahead and set up our 2 possibilities. And you might think that there are 4 possibilities. Well, you know, this could be positive or it could be negative. This one could be positive or it could be negative. So there's 4 different combinations, but it really works out to only 2 unique possibilities, and they're going to look like this. So in this case, we'll set this up as 3x minus 2 is equal to 2x plus 7. So the possibility that they're both positive, or the possibility that one of them is negative. And I'm just going to make the first one negative. So 3x minus 2 is equal to 2x plus 7. And then we just solve these 2. So let's see. For the first one, let's go ahead and subtract 2x from both sides, and then I'm going to add 2 to both sides. So these will cancel out, these will cancel out, and I'll have a positive x is equal to 9. So perhaps that's a solution. And then we'll go ahead and we'll distribute this negative. So we have negative 3x plus 2 is equal to 2x plus 7. And again, we're going to get our x's on one side, and we're going to get our constants on the other. So those cancel out, and we've got minus 5x is equal to 5. And if we divide both sides by a negative 5, isolate the x, we get x negative is going to be equal to negative 1. And again, if we don't believe it, we could check the solutions, but both of those end up working out. So that's how we would do the problems in number 1. So let's go ahead and move on to the second problem on this worksheet. And here we're asked to sort of put together the graphs of these absolute value functions that we're given here. One thing to maybe keep in mind as we're doing this is we could sort of dip back to the skills we picked up in 1.7 about graph transformations to sort of interpret these functions as how has the absolute value function, which we know looks like this. This is just sort of a general function. If we had y is equal to just plain old absolute value of x, we know that this is sort of makes a v at the origin. So this is what we start with, and then we're going to kind of go through and make various transformations to get different looking graphs. So let me go ahead and get that out of the way. Okay. So this first one, let's actually think about what this would look like, or what type of transformation has occurred. So if we started with just absolute value of x, and now we've got this 4 added on the inside of the function, this implies to us that the absolute value of x has been shifted to the left 4 units, because we're adding a number inside of the function. So this is indicative of a left shift. So the graph that we end up seeing should look like that characteristic absolute value of x just shifted along the x-axis 4 units. Let's see if that works out, and we're going to do that by finding the x-intercepts and the y-intercepts for each of them. So let's go ahead and do that next. We'll start with the y-intercepts. So the y-intercept we know is most easily attained by just taking our function f and evaluating at x equals 0. If we do that, we're going to get the absolute value of 0 plus 4, which is just going to give us the absolute value of 4, which is just 4. So we're going to have a y-intercept at positive 4. And then for the x-intercepts, the way that we do that is we take our function, we set it equal to 0, and then we solve this for x. Now we know that in order to solve an absolute value equation, we break this up into two separate ones. So we're going to go ahead and do that. So we've got x plus 4 is equal to 0, or minus x plus 4 is equal to 0. We solve each of these, we get x is equal to negative 4. Here we distribute the negative. We add the 4. And then we multiply both sides by negative, and we get x is equal to negative 4. So they turn out to be the same thing. So x equals negative 4, x equals negative 4. We've only got one x-intercept. But now that we've got these values, we should be able to put together a pretty good graph based on what we know. So we'll go ahead and we'll set this up. So here's our x-axis, here's our y-axis. Y is equal to the absolute value of x plus 4 in this case. So let's go ahead and mark our important points. So we're going to get the y-intercept at 1, 2, 3, 4. And then we've got our x-intercept at negative 1, negative 2, negative 3, negative 4. And we know that this is going to have x-intercept, y-intercept, and that this curve is just going to be that v that we're used to seeing with the absolute value. So this is basically our curve, and we've got that just from a little bit of knowledge about the few points here. All right, so let's go ahead and try that with this next one, part B. So we've got the function being the absolute value of x, and then on the outside we've got minus 3. Now in terms of graph transformations, you should be able to look at this and say, oh, you know what? We've taken the absolute value of x, and we've done is we've shifted it down 3 units, because we've subtracted a value outside of the actual function here. So let's go ahead and calculate the few points that we were asked to. So the y-intercept, all we do is we calculate the function evaluated at 0, the initial value of our function, and that's going to be equal to the absolute value of 0 minus 3, which will just be negative 3. So we're going to hit the y-axis at negative 3, and then for our x-intercepts, we're going to take our function, absolute value of x minus 3, set it equal to 0. Now here's a great chance for us to do that first step that we alluded to on number 1, is we want to isolate the absolute value function before we break it up into 2 separate equations. So let's go ahead and do that. We'll add the 3 to both sides. So absolute value of x is equal to positive 3. Now we look at our 2 possibilities. Positive x could be equal to 3, or negative x could be equal to 3, which gives us minus x equals 3, or x is equal to negative 3. So now we've got 2 x-intercepts to consider here. So let's go ahead and get our graph together and see what we're going to be looking at. So we've got our x and our y axes, and we've got our y-intercept at -1, -2, -3. We've got an x-intercept at +1, +2, +3. And we've got our other x-intercept at -1, -2, -3. Sorry for the not so precise scaling, but you get the idea. So we'll go ahead and we'll plop these down. So y-intercept, x-intercept, x-intercept. We know this is going to look like the characteristic absolute value v. And this looks exactly like we would have expected to if we had considered the transformation. It's the absolute value function just shifted down 3 units, and that's what we're looking at. Okay, so for the last one, we've got a couple of things going on here. So what are the transformations that we might think are occurring here on the absolute value of x? So this is the absolute value of x, and we've got 2 things going on. First is that negative out in front. That's indicative of an x-axis reflection. So we've got the absolute value of x reflected over the x-axis. And we've also got that 3 out in front of our function. And having a constant multiple outside of our function tells us that we've got some sort of vertical scaling going on. So this has been vertically stretched in this case by a factor of 3. So let's go ahead and get some points and see if this actually turns out to look the way that we might think it would. So we've got the y-intercept, calculate f of 0, which is going to be -3 times the absolute value of 0, which is just going to give us 0. And then our x-intercept, we take our function, set it equal to 0. Now we can look at this and we can see the only x value that we could possibly pick to plug in here, positive, negative, whatever, is going to be 0. So our solution here is just going to be x equals 0. So our y-intercept is 0, our x-intercept is 0. Both of them are the same point, the origin. So this is not going to be completely helpful for us in terms of getting graphs, so we're probably going to need to get some other points here. So there's the one point that we do know, the origin. One thing we could do is we could maybe just pick some extra points, like we could pick x equals 2 and see what happens. So if we picked x equals 2, we know that f of 2 is going to be -3 times the absolute value of 2, which is -3 times 2, which would be -6. So we could at least put another point there. Why don't we go ahead and do that? So when x is equal to +1, +2, we're going to go down to -1, -2, -3, -4, -5, -6. So I'm just going to go ahead and put that point there in green. So that's an extra point. And let's just go ahead and do one more to get the symmetry. So x is equal to -2. And you could have picked +1, -1, +1, -3, 1, 8. It really doesn't matter. But I think getting these points is going to help us graph it a little better. So we've got f of -2, which would be the -3 times the absolute value of -2, which would just be -3 times 2, which would be -6, which -1, -2, which would give us this point right here. And if we were to connect the dots to get our curve, we would see something that looks like this. And this is exactly what we expected. We've got that absolute value v reflected over the x-axis and then vertically stretched by a factor of 3. Okay, so that'll do it for this worksheet, and I'll see you all in the next one.